direction. So if you actually push it along direction, nothing will happen, right? There's this extra degree of freedom that the cells will get compressed, but overall, there will be no strain in the perpendicular direction, right? So I give this example. This is like very intuitive example in terms of like a structure property relationship in material science, because in material science, what we are trying to do is to identify this feature, this salient feature, this like a characteristics that directly controls your property, right? And unless we can see the structure of the material, it's like really difficult to hypothesize. So what is really causing this like peculiar behavior, right? So this is the example of cork. This is the cork that is being like pulled in one direction. So what you see in the image to the right. So remember, there's always something about the structure. But microstructure you can also see in bread. So when we eat, we have like the sensation. We eat, we like certain food, we don't like others. So there's like a microstructure you can also see in bread, in our bones. The reason why we like animals are so light is because most of the bones are empty inside. Nevertheless, they are strong, and you see those like beans inside our bones. Those are the reasons why we have like decent like we have like a bones that sustain like a load, right? When we walk, when we move, and so on. And if you look into the skeletons, because this is yet another example of the structure, if you look into the skeletons of different animals and you look into those like bone structure, you can again find certain characteristic. Let's say the ratio of the bones can tell you if given like animal will walk on 2 or on 4 feet, or the animal will fly, because then you have like the ratio of the bones will be different. So there is always something about the structure that controls your properties, right? So this is the basic concept of material science that we would like to understand what it is. But microstructure, or the structure of the material, has like much more applications. This is like some of them. So this is the aerogel that is made from really small silica particles. And the volume fraction of particles to the entire volume of the material is really, really low. So it's less than 1%, right? So this, and even though the volume fraction is so low, the properties are still relatively good. So one of the amazing properties is low density and low weight. This makes it ideal application for aerospace or NASA application, right? We want to select the cost of sending any material to space is really high, so we want to lower the weight, but at the same time, we want to like maintain certain properties. Another application of this heterogeneous microstructure is lithium-ion batteries. So what you see here is 2 electrodes that are porous, and the porosity here is because when ions or electrons are traveling between 2 electrodes, there's like a surface area that promotes the entry of the electron and ions, and we want to maximize the surface area here, right? At the same time, we want to provide the continuous pathways. So there's like an interest in understanding or even designing those like microstructures of the porous materials. Right? Looking closer to the nature, when we look into the structure of the leaf, the surface of, let's say, lotus leaf is interesting. When you zoom into the microstructure, you will see those pillars, right? And those pillars are interesting because they have this like they provide when let's say the droplet of water will land on the surface, they provide the suspension, right? But additionally, if we zoom in, we'll see those pillars are additionally coated with a kind of wax, right? So that the water will not want to stick to those pillars. So again, by looking into microstructure, trying to understand what really controls the properties. The application that I am most interested in is organic electronics. So those are the devices that are made from plastics or from polymers. They are very light, they are transparent, and they can be flexible. So you may have seen those pictures of like solar cells that you can coat literally on anything, on your clothes, windows. You can take them for like a backpacking trip and so on. This is more exotic, like which is the cell phone you can like fold and put in your pocket. And I think we are moving closer towards this those applications, but there's like few challenges that we need to address, and one of them is microstructure. So what you see here is the image, tomography image microstructure of solar cells, or the active layer of solar cells that consists of two materials, electron donor and electron acceptor. So they are marked like a black and white here, but yellow or orangey and black in the 3D image, right? The microstructure is sandwiched between two electrodes, and there are like few reasons why we want to have this nice interpenetrated structure, but there are still many challenges in terms of even visualizing the structure of the active layer, or even understanding what is this waviness of the solar cells that controls properties. And first, it would be great to visualize, but the thickness of those devices is like 100 nanometers. So visualizing microstructure is a challenge in itself. Okay, but those are like many applications. So in general, the holy grail of material science is to link the process, because we need to know how to make those materials, right? So we would like to understand the function that links the property with the structure. So let's say structure is this like cork structure, and there's this waviness. So we'd like to understand what is this descriptor or some feature of the structure that controls the properties. And then once we know what is this feature, we would like to also understand how do we design the process that will give us the structure, right? So this is like a high level abstraction of what we want to figure out in terms of designing materials. We would like to learn those functions F and G. We'd like to somehow parameterize the structure in order to even construct those functions, right? So if you want to like map structure to property or property to structure, you would like to have a low number of design variables that you would like to choose from, right? So at the end of the day, would like to invert those F and G to design the process that improves the property. So this is the high level. So a few examples here. Coming back to this organic electronics, so let me walk you through basic steps of the fabrication. So what you see in the right here is the pictorial representation of the process. So we are starting with the solution. So solution consists of three components: electron donor, electron acceptor, which is like polymer and let's say fullerene, and they are mixed together in a solvent. Okay, and they are mixed together in the solvent for a good reason, because solvent provides this environment for them to spread on the substrate. And then as we spin the substrate, the polymer and fullerene, or donor and acceptor, will interact with each other, and solvent will be gradually removed because we are spinning the substrate, and the solvent is chosen in such a way that it likes to like evaporate, so it's very volatile. And once the process is finished, you will see this like structure of the thin film. Okay, so there's no solvent here, there are only two materials, there is some internal structure, and this internal structure is important for the properties, right? So if you would like list all possible design variables that goes into this relatively simple fabrication process, you will end up easily with 15 process and system variables, like evaporation rate, choice of solvent, choice of polymer, or even the thickness, temperature, and so on. There's easily 15 to 20 parameters that you may change. It's like with the cooking recipe, right? So there may be like many different variables. So there is a large design space for exploration here. And current approach is trial and error. And as Dr. Rai mentioned, as of now, there's like a luck, right? So someone will go to, many of the advances were made by luck, by pure luck. So someone changed something and suddenly the properties improved, right? So here, when it comes to challenges and opportunities for this application, there's like a decision-making process to be made, or the application for artificial intelligence. If I have, let's say, 3 different processes, so those are results from computational model of mine, and there's a difference in terms of one parameter here between those 3 different simulations. And as you can see, as solvent is removing the system, we have like a gradual formation of the phases. Details are maybe not that important, but like one change in your design parameters resulted in the completely different final microstructure, right? So we would like to be able to explore this design space in a smart way. So this is one of the challenge in the material science, that we really need to find some good way of exploring. Another project that I am interested in is like 3D printing and data-driven approaches for accelerating the design of the fabrication process. So 3D printing is this like exciting fabrication process where you can automate it, right? You can program a robot, you can program the machine that will gradually deposit your 3D part, however complicated it is. It will gradually deposit the material, and you will get this like 3D structure. Applications is like personalized medicine. So if you want to rebuild your bone structure, or you want to build some medical application, you can literally scan your body and then build it. So when you think about it, this is like a relatively simple process. The robot can automate it as of now, right? So the moment I have 3D STL file, I can like slice it into layers. I can then design the toolpath deposition, and robot can execute it. So it would be like interesting to think, okay, can I actually build a computational model? So can I build a simulation tool that will be, rather than printing, I would be able to predict the properties, or even the temperature distribution of the process, right? And currently it is actually faster to print the part and test it rather than predict the behavior of the part using computational model. But when you think into, let's say, this relatively simple geometry, right, and you see the position path, right? So if you focus on one point P, and you draw the temperature distribution, you should be able to guess that the moment I have the next layer deposited, my temperature here will increase, right? So there are those like, there is like, given the path or the way you deposit the point, you should be able to even predict those like increase in or changes in the temperature of the part, right? So the observation here is that there is a high redundancy in the process. The process is automated, and this is like one of the applications for machine learning, right? Because there is this potential redundancy in the process. So there was like one paper from my group that actually addressed this problem, and we can build this model using those characteristics of the deposition process to predict temperature, or and then to predict the properties of the part. So this is like one applications for AI or data-driven approaches in this context. But like the rest of the talk, I would like to talk about the link between properties and the structure, right? So let me start with this periodic table. This is like a periodic table that was proposed by Mendeleev 150 years ago. And think about it, 150 years ago, we didn't know how the atom looks like. Yet Mendeleev could like organize elements following some group and period organization. And at that time we didn't know, and he did it mostly, he did it based on the properties, right? So he said that some of those atoms have really similar atomic volume, so most likely they will have some similarity. At that time, he didn't know that, we didn't know gallium, but Mendeleev was really bold. He said, okay, even though we don't know that there was this element here, right? But I think it exists. We just don't know it exists. So what he did, he said, because it's so close to aluminium, he called it eka-aluminium. I mean, in his organization of the table. And he even predicted that the atomic weight will be 68. right? So things, and few years later, indeed, the gallium was discovered, and his prediction wasn't far away. So this is the example of the machine learning in the early phases, right? The brilliant mind of Mendeleev was able to organize the data without understanding the structure of material. So if we could repeat it for other types of materials, this would be like one task to go with. So as we move to, let's say, molecular level, molecules becomes more complex, and there's like more features rather than thinking about group and period. There's definitely much more features, right? So there are lots of software that allows you to calculate descriptors for molecules. Dragon is my favorite one. Given a molecule, it can featureize your structure into 5,000 descriptors, which is amazing. When you look into the microstructure level, so one level up, no such tool exists. Yes, there are like tools that allows you to characterize some aspect of the microstructure. ImageJ is like a very good example. There's Aviso, there are like other tools, but there's no tool that you take a microstructure and you featureize it and make it ready for the machine learning workflow. And this is like a challenge in terms of microstructure informatics. We don't have well-defined pool of descriptors at microstructure level. And at the same time, microstructure is high-dimensional data point. Easily, it can have millions of pixels. And remember, the success of machine learning depends on data representation, right? So we want to be able to somehow represent the microstructure. And if you like look into what is really important, the data wins over model sophistication. The more feature we have, the better, because then we can use tools of feature selection or feature engineering to narrow down number of features that are really important, or we would like to find this like waviness of the cork, right? And what is our approach? We would like to use graph-based representation to create those descriptors. So how do we do it? We start with the black and white image. So let's say this is like a two-phase microstructure. We take every single pixel represented as a vertex in the graph. We color code the vertices based on the phase it belongs to, and then we connect them via edges. So in this case, the edges are trivial because every voxel will have north, south, east, west neighbor, and then the second order neighbors, right? So we can create the graph. But why do we need the graph? It's because we want to quantify some features. So let's say if we apply the graph filtering, and in our input graph will mask all edges that connects phases or vertices of different colors. So we just remove it or we mask it, right? And then we can ask the question, find me all subgraphs in my network, right? So find me all, let's say, subgraphs that are of white color. And here it will be 1 to 3 white subgraphs of connected components, and then 3 black subgraphs of connected components. And then we can start asking the question, okay, can you find me how many of those connected components of subgraphs are, let's say, connected to the bottom electrode, right? Here, the bottom electrode is marked with red color, right? And we can build those descriptors, or we can featureize the microstructure with set of numbers, right? The moment we have a set of numbers, we can start to apply the classic methods in machine learning. So in my group, we are developing a tool called Graspy that computes wide range of descriptors. Some of them are morphological, some of them are topological. We can add like, we have like a comparison of statistical descriptors, weighted descriptors. So those like, we are not at the level of Dragon where we have like 5,000 descriptors, but we are somewhere around 100 descriptors, right? So as we have more applications, more properties to work with, we can easily expand those descriptors. So let's look into one example. I know that I should slowly wrap up, but let's look into those microstructures. So we have like example microstructures that would like to understand what is so special about those microstructures that correlates with our properties. So we have a short circuit current, which is like JSC, and we have a microstructure annotated with a long list of descriptors. Here we have 21 descriptors. And what we would like to build is this function f. So we'd like to define a short circuit current as a function of descriptors, and like those descriptors to be the number of descriptors to be much lower than the input 21. Okay, so that's the goal for us. And in 2014, between 14 and 18, I was like looking into those descriptors manually. So I was looking into the model that allows us to predict the short circuit current. And I was trying to manually define those descriptors, and I was trying to identify those that are really important. And I was successful. After months of working, coming back to this problem, I identified 3 descriptors. And for every single microstructure, which is depicted as a point here, we could predict the short circuit current, and then a product of 3 descriptors manually selected. And it turned out that the correlation was really, really high. We were very happy. And then we started asking questions. So we know those 3 descriptors. So can we optimize the problem and determine what microstructure actually gives you better properties? And those are the 2 examples that we found. But this was like a few years ago. And as I said, there was a lot of work put into this like 3 feature determination. So recently in my group, we asked the question, so can machine learning replace the expert? Remember, there's lots of work behind identifying those 3 features. So we use tools of feature selection, which is a classic method in machine learning, which is a process of selecting most significant relevant features from the large set of features, and ideally K should be much, much smaller than D. The simple method here is MRMR, which stands for minimal redundancy and maximum relevance, because that's what we'd like to do. We'd like to find a descriptor from the initial pool of descriptors that carries a lot of information in terms of link with your properties. So there's a high relevance, but at the same time, minimal redundancy. So the method is relatively simple. So you start with the initial set of features. You look for the correlation with your property. You find a descriptor that is most correlated with your property. You put it into your bag of features. And then in the next iteration, you look again for the feature that is like most relevant, but then you check the redundancy with the features that were selected. You calculate so-called importance score. And this allows you to order your features based on their importance, right? So this is like out of 21, we're able to order them based on this importance score. And when we build a model or linear model as a function, so for a different number of features, we look into the performance to R-square value, and it turned out that here maybe 5 features are important, right? So it has like a relatively high performance. So we asked this question, can a small subset of features be selected? And the answer here is yes. And remember, the experts said that they are 3 features. Machine said they are like 5 features. And the performance is really, really comparable. We tried different feature selection algorithms. They all gave us very similar number. And we also asked the question, can the expert identify or like enriched features improve our model? And the answer is yes. So I was really happy with those results because it shows that yes, we can replace the expert to some extent. We can automate the process. The process can be much faster. The set of features are very similar, and it's independent of the method that we use. So to conclude the talk, I was thinking about saying few things here. So what is my view of the future for computational material science or computational physics and materials informatics? So we have many of work in materials informatics is focused on the atomistic level. There's this term chemoinformatics that is like widely used in chemical engineering and chemistry. There's a lot of work done there, a lot of impressive work. But I think what needs to happen is that we need to now shift into the high level, which is microstructure informatics. I think we also need like a shift in terms of paradigm, in terms of physics-based modeling. Computational models and experiments are expensive, and we need some way to accelerate the process. So building different surrogate models would be great. And something I didn't talk about is data consolidation challenge. So we are good in terms of generating data, but those data are generated for very specific applications. We can build surrogate models. The one I showed today is just one example. But if I have, let's say, 2, 3, or 100 different data sets, how do we consolidate? So I think we need to also start thinking about it, about generalizability of our models. If we train the model for one data set, can we really use it for another data set? Or under what conditions we can use it? Or how many experiments we need to take in order to be able to transfer? And the last one, I think that's one of the reasons why you are all here. We need to train new generation of professionals who are skillful in terms of data analytics, machine learning, and material science. And I will stop here. So I will be open to answers later on, but this is my view on the topic.
Thank you very much, Olga, for insightful comments and very, very exciting projects. Let's welcome our next speaker, Saeed Farahani. Saeed will be talking about his research at the intersection of manufacturing, computational material science, and AI.
Hello, everyone. Hi, Raul. How are you? Yeah, good to see you again. So, how much I have time? So that I
20
can
minutes, 20 minutes roughly.
20 minutes. Okay, great. So let me, I guess you need to enable me.
Which I have already done as a co-host.
Okay, co-host. Okay, sure. Let's go. Can share. I guess.
Somehow we have lost our speaker, so we wait for him to rejoin. Meanwhile, Saeed is trying to join. Olga, I think we can continue this discussion for our attendees. According to so he has joined back. Again. So I made you co-host, Saeed. You are muted, so somehow we are not able to hear you. Yes, we can see your screen too.
Okay, can you hear me also?
Yes, we can.
Yeah, sorry about that. So I guess there was some like a setting that I changed it, and then after that it asked me to restart the Zoom again. So yeah, so I'm basically presenting this presentation on behalf of Dr. Pila. Before joining Cleveland State University as assistant professor, I used to work at Clemson University as a research assistant professor. Before that, I was postdoc and also PhD student. All the time I worked with Professor Pila, and this part of the work that I'm going to present today is the majority of that has been done during my postdoc. So that's why, because of the kind of something urgent happened for him, so he asked me to present this work. So today I'm going to introduce you the concept of Composite 4.0 and talk a little bit about our research in this research direction. So this is, first of all, we need to acknowledge from our research group. So it's a big research group. And as you see, I'm here also. In that time, I was in Dr. Pila's group. And this research has been supported by SCRA, South Carolina Research Authority. Before going to the research project, I need to talk about what is Composite 4.0. Basically, Composite 4.0 is an application of Industry 4.0 in plastic and composite manufacturing. So you know a lot, you have heard a lot about the Industry 4.0, but something which was very basically a key technology for us was the connected system. Because if you look at each individual technology which in the collection of the Industry 4.0, these are but not very new. For example, if we talk about the machine learning has been around for more than 70 years or almost 100 years. If we talk about the basically a cyber physical system, it's not also new. We always has like even in a simple injection molding, we have integration of some software with the hardware. But the thing which makes different is the connectivity, which if we have multiple equipment, multiple devices, multiple sensor, and we connect all of them together in a two-directional, connection, read and write, then that makes different. That's why we focus more on connected system in developing the concept of Composite 4.0. But why we need basically Industry 4.0 or such kind of technology in plastic and composite? So there are two sets of reasons for Composite 4.0. The first part comes from the complexity of the manufacturing process in plastic and composite. For example, if you look at the equipment, if you compare a stamping press with injection molding, you see that how much injection molding is more complex in terms of having a multi-physics condition in those equipment. We have a polymer material in a solid phase, goes under a thermal condition, goes to the molten state, and then we have injection process, which is a complex fluid mechanics condition, and then we have solidification, and at the end we have a solid part. In terms of the another complexity comes from the heavily human-based process. For example, these two samples that you are seeing at the bottom of this slide, it's a final project delivered by a student. So we gave them same material, we gave them same basically fabric, resin, and they use same equipment. But as you see, the quality of the part that they manufacture is significantly different. The reason is that the difference between human expertise, So this is also another part of the complexity of this process. And if we can, in any way, reduce this complexity using these new technologies, such as we call it Industry 4.0, that would be very beneficial for plastic and composite manufacturing. If in any way we can reduce human intervention, if in any way we can reduce the effect of human expertise in the quality of the component, so it would be very beneficial. Another reason for Composite 4.0 comes from the industry need. As you know, composite material and high performance plastic, they have superior properties, but their main drawback is their cost. Okay, is their high cost of material and manufacturing. So in any way, if we can reduce the cost of the material and their associated manufacturing process, it would be very beneficial for this in order to expanding the application of high performance plastic and composite in different industry, especially in automotive industry, because it's a very cost driven industry. So if we can use this technology to accelerate development of the material, if we can basically reduce human intervention or come up with more flexible and manufacturing process that we can fulfill the requirement of mass customization. Okay, now we know what is Composite 4.0 and why we need Composite 4.0. Now let's talk about the how we can implement Industry 4.0. Basically, this is a kind of a route map, a flow chart that we follow we have followed for particularly for developing the concept of Composite 4.0 in our lab and in our research. But it was initiated from the actual manufacturing environment, so the idea. So as you know, in composite and plastic manufacturing, similar to other industry, we have a variety of machines and devices. Also, we may have some external sensors, or we could install some external sensors. Also, we have some manual operation, such as manual fabrication, post-processing, quality control, and etc. So if we can integrate data from machines, different machines and devices, sensors, and manual operation, and more importantly, unify data, then we can use that unified data and transfer that unified data into information, into actionable information using any kind of like knowledge base or physics-based models, statistical or machine learning models. Then we can transfer that information as a feedback to the equipment and make a closed loop control process, or we can use that information to build any kind of manufacturing system, such as manufacturing execution system, or even we can send that information to the highest level of enterprise to make a decision based on management decision based on the real-time data from manufacturing level. So, but something that we shouldn't forget is that the ultimate goal of all these basically implementation procedure is to bring added value for that business, and the level of that value and the amount of that value should be proportionate to the effort that we need to implement these technologies. So now I'm going to talk a little bit about different sections of this this basically the implementation flowchart. First, let's talk a little bit about machines and devices and see what are the challenges at this level. So at this level, the main challenge is the existence of the legacy equipment. You know, in plastic and composite manufacturing, similar to other manufacturing environment, we have a variety of different legacy equipment that they work perfectly, but the only issue about them that they have been manufactured without any connectivity or sometimes sensing features. Another challenge is that we have variety of different sensors and external sensors, in-mode sensors, but there is no rigid or a specific criteria for selecting the sensor for different application. Actually, based on that, we have a study in terms of evaluating different data sources in injection molding, particularly in a collaboration with Kistler, and that the result was published, as a paper in a collaboration with the Kistler authors. Anyway, if we have any legacy equipment, so there are a couple of approaches to integrate those legacy equipment or even some simple devices with a normal communication port. We went through this for different equipment. For example, for one of our injection molding, although it wasn't a very old equipment, it was like 2014, but the communication protocol was Euromap 63, which was like a text-based communication protocol. We went through two procedures. One procedure was just to customize the interface using two different software, and we convert that old protocol into new protocol, which is basically OPC UA. The other approach was to use some cost-effective IoT solutions. Particularly, we use a PLC gateway from Behertek. It's a wireless technology, and using that, we could directly get data from PLC and connect it with through the network. In terms of the external sensor, I mentioned about how there are a variety of different sensors and the challenges that when and where we need to select that specific sensor. I will talk about that a little bit as one of our case studies. Now going to the unifying and storage. So the challenge at the level of the unifying, the main challenge is that we have a variety of different sensors with different data, with different data types. And combining them while we are keeping the spatial and temporal correlation of the data is very important. Just to give you a simple example, for example, when we get the data from extrusion machine, extrusion is like a time base, is a continuous process. On the other side, we have injection molding machine. Injection molding is like a cycle-based process. So now we want to integrate these two together, these two data together. Why we want to integrate? Because we want to know that, okay, this piece of the material which went through the extrusion process, and then after that was used in injection molding process, how these two, how we can correlate that data with the data that we get from injection molding. So now it's very important to know exactly that, okay, this piece of data that you get from extrusion machine is correlated to which part of the data that you get from injection molding machine. Or even if you have an external sensor, it's exactly the same thing. Some of the data is like a time-based data. Some of the data is discrete data. It's just a point data. Integrating these two types of data are also very challenging. And then at the end, when you integrate data, it's a massive amount of the data. For example, in injection molding, for each cycle and for each data source, we get almost like a 3,000 point. So imagine 3,000 point of data for each cycle and for each data source. How much is going to be the size of data after 1 day operation? So how to store this data and then later have access to that data, it's also very challenging. We particularly, for that, we explore different options using data acquisition system, using distributed control system, or supervisory control and data acquisition, or SCADA system. And we found out one of the best options in order to integrate data from variety of different equipment and sensor is using SCADA software. Particularly, we use Ignition software for data integration, and it provided us a very unique features for data integration. Transferring data also was very important. We went through different strategies in terms of how to extract the features without missing any important part of the data, and then later how to analyze those extracted features, and then how to develop model considering the long-term use of that, how we can improve the model in a long-term process. So this is like very kind of talking about the different approaches that we went through, supervised and unsupervised approach, and different modeling strategy. Particularly, we focus on hybrid approaches, combination of physical-based with the statistical modeling, or like some black box algorithm, machine learning algorithm. Combination of them was very interesting for us, and we were interested about these combinations. Something we call it physics-regulated machine learning. And one challenge is embracing this technology by industry. We actually work in separated proposal how to educate industrial people in order to better embrace this new technology. The first step was to teach them how to basically retrofit their equipment, and the second step was to how basically use this new technology in their day-to-day operation. We work with some technical college in this term. Anyway, there are some examples of implementation of this, as you see, integrating multiple injection molding data from the material sources, and also some wireless sensors from water storage and water cooling system. So let's go particularly and reach to this, because I know we have a limited time. This slide is one of the important slides, which shows the status of connected system in our lab. As I mentioned, for connecting different types of the equipment and devices, we use ignition software. And as you may notice, these connections are all two-directional connection, read and write. And we could even connect some simple devices such as scale using serial port, and that connection was even two-directional. And we could write, and we could send a comment to the scale that, okay, what is the weight at this time, and then getting that number. So this is actually the beauty of implementing this technology, because at the same time, even we connect some of our software. So I forgot to mention that we connect some of our software, particularly MATLAB, because MATLAB has OPC UA server, so an OPC UA module, and through that it's possible to connect software also to this system. The beauty of this system is that at the same time we can get one data from this equipment, one data from another equipment, one data from a remote sensor, calculate something at a real time, and send feedback to each of these equipment. So based on this, at the first step, I'm just going to wrap up this discussion with one of our example or case studies that we have done. So by integrating data from in-mold sensor and injection molding machine, so at the first step, we basically explore the possibilities of using this integrated data. And the idea was that, for example, in terms of the quality control, usually people try to control the quality of the component based on the initial parameter setting. But we have too many parameters in injection molding. And if you consider the interaction of these parameters, it's a very challenging process, and it needs too many experiments to find the optimum condition. But instead of that, if we focus on the real-time process data, which are significantly lower in terms of the number of the data, so then we can more efficiently control the quality of the process. As I mentioned here, like instead of initial parameters, we focus on online process variables. One of the first study that we have done was evaluating different data sources. We integrate almost or exactly 12 different data sources from injection molding and in-mold sensors. And that was the study that I mentioned. It was collaboration between Kistler, Clemson and Kistler group. And we basically, at the first step, we realized that after this integration, we cannot use with the integrated data because it's huge. As I said, just for one single data source, it's 3,000 points. And that's why we develop a feature extraction. And the first feature extraction that we developed was a knowledge-based feature extraction. We basically develop a program and we extract some point of interest based on the physics or based on the knowledge that we know about the injection molding. For example, the maximum is the pressure at the end of the injection phase, or this part. The BP5 is the packing pressure, or BP7 is the plasticizing pressure. So by knowing this expert knowledge, we develop a program to extract these features, and we could significantly reduce the dimensionality of the data. And also we use like a simple partial least square regression to find the basically importance of each extracted feature. So and we rank these data sources in different process perturbation. For example, in terms of shot volume variation, or in terms of material disturbance. So intentionally, we add the different percentage of the different material into the base material, and we see which data source can faster and more accurately detect this process variation, and how we can, and which data enables us to more accurately predict the quality of the component. We basically invest, or we look at three quality indices: weight, thickness, and diameter of the injected part. So just to give you an idea, I guess we are reaching to the end of the presentation. Just to give you an idea, for example, about the barrel pressure. As I mentioned, initially it was 3,000 point, okay? So we develop a knowledge-based feature extraction. We extract point of interest. Among these, like 9 point of interest, one of them was BP2. And then through this data analysis, we find out that BP2 has the most correlation to the weight of the component. And as we demonstrate here in a graphical representation, it is exactly following the weight of the component, but in a different direction, just to verify that result. But other features doesn't show any specific correlation to the weight. What does it mean, this result? It means that among all these 3,000 points, if you just monitor one single point, you can perfectly monitor the weight of the injected part. Such kind of outcomes are very valuable, because there are some network technologies such as MIoT. It's a long range, low power technology, but the limitation is the amount of the data that you can transfer. If you can significantly reduce the dimensionality of the data and reduce the dimensionality just to one single point, then such kind of technology would be perfect for implementing data-driven quality monitoring system or any kind of similar system. So I kind of finish this discussion by this example. And please let me know if you have any question.
Thank you, Saeed, for a very, very insightful project and sharing your work at the interface of injection molding and machine learning. This is very good to know that you have like such an integrated system already at Clemson, which is generating a large scale data sets. So with this, we are very close to the finishing the overall webinar. But one final question I want to have for both the panelists is that, we do have a lot of students in our audience who are interested in working at the interface of machine learning, data science, and AI. And today's topic has been computational material science. So to both of you, what emerging skills do you recommend for students who want to enter the space, in the space of AI, machine learning, data science, and possibly in computational material science?
So you want to go first? Or should I go? How do you feel?
Yeah, you can go
okay.
Go ahead. Okay.
So I was thinking about it in the context of panel I run myself, and I kind of always ask this question, and I think this is the important one. I would say that automation will be more common in data science in general, right? We'll have tools that will be like, and with sklearn in Python, we see already this, right? You have a function, you execute. And I think it's more and more important that you have an expert knowledge, that you have understanding what is happening on top of your knowledge in terms of data science tools, right? Because you will get a number, but this number must make sense, right? So I think it's equally important that you put an effort into understanding the underlying processes, that you have some knowledge, I think that the good data scientists are data scientists who has some background in other engineering field, right? So let's say material science, plus data science, right? Or mechanical engineering plus data scientist, right? This like knowledge transfer from expert field will be very, very important. So I think I also saw it in the other talk that expert defined features allows you to get like a really high prediction from the model, right? So I'd like to stress out, don't focus only on executing the code, right? Try to learn something about the underlying physics. And I think this will give you the edge when it comes to competitiveness.
Very well said, Olga. Any inputs from you, Saeed?
Well, yes, as Olga just said, so I guess combining the physics-based knowledge with the data science is really interesting. As I mentioned also during our work, we try to focus in hybrid approaches, combination of physics-based models with the machine learning, with AI. Those would be more, effective and efficient, in terms of developing any kind of data-driven systems. So that would be definitely important. Another thing that I would like to emphasize is data integration. Getting data from one single sensor is not something new, okay? It has been around for more than, 50 years or more, okay? The new technologies enables us to integrate data from multiple sources. So I really recommend new scholars to go towards data integration from multiple sources, and they see lots of benefits from that, And something, just a quick example I can tell you, that we integrate data from injection molding and in-mold sensors, but none of the data was related to temperature. It was all pressure or displacement, okay? Using that integrated data, we could predict the temperature inside the mold. That is very interesting. You don't have any data about the temperature. It's all pressure and displacement. But using the integration of this data, we could predict temperature. We have a study, the paper is going to be published soon, which is the result of this study. So thank you.
So I would really like to take this time to thank both the panelists, Olga and Saeed, for taking out their valuable time to disseminate the information and the knowledge that they have to a broad audience. The audience focus is obviously data science, AI, and machine learning, but due to your knowledge, we were able to at least talk about what this sort of techniques and what is their meaning in the context of computational material science. With that, I thank you all the attendees and the panelists, and we will again continue this series later on, and I will have LinkedIn post and Facebook posts related to the next set of webinars. With that, thank you and bye everyone.
Thank you. Bye. Nice meeting you all.
Nice meeting you all. Bye.